Hello, today we will talk about how to conduct real-world projects and if you're a mathematician, how to survive them. So the first question is, what does research mean? This is important because here is a fundamental difference between what you as a researcher want and what industry expects. Research basically means that the outcome is not yet determined. We don't know the result. And it's very much possible that a research project ends showing that it's just impossible to achieve the goal. And you do this by systematically trying untested methods. And so in the end, it's always possible for a research project to end like this. And this is definitely not what any of your industry partners wants. And they will do everything to ensure before against this happening. And this is a topic where you have to think about how much you can promise and what to do. Let us talk first how to get the project. How do you convince industry people that you can help them? I mean, mathematicians not necessarily have a reputation that if you have a real-world problem, you go to a mathematician and he will solve it for you. So the first thing you have to see is that they are the specialists for the topic, not you. I mean, they might have been working on this for 20 or more years, some companies for even longer, and now you come there from university and say, oh, we know better how to do your business than you. This is not very convincing to start with. And they don't want a result that says we can prove there exists a unique solution, but have absolutely no clue how to find it. So this is something you have to keep in mind. And well, even if you know something about their business, regardless whom you ask, they will tell you we are special. From a mathematical point, of course, if they're all special, they're all equal, but nevertheless you have to somehow adapt to what is special with them and compared to their competitors. And and if you try to show them that you already did something similar, they might have a very narrow view on what they did and with little abstraction. As a mathematician, I can go and say, well, you want we should optimize in a container harbor. Well, I already optimized internet packets on a router. It's pretty much the same. You have these packets, they go through, they are discrete and everything, but this is not the view that somebody optimizing or working on a container harbor will have. And then finally, always there's a question, how much can you improve by using mathematics? And there is a very nice answer from Gunter Duck, which was published in the DMW-Mitteilung, and the correct answer is always 15%, and I will show you now how. So the improvement potential is always 15% because if you say, well, 5%, then the manager will say, so much we can save by simply pushing the employees. If we say 10%, they say, well, it sounds poor. We could do similar ourselves, and if we get as much money as you, we can do this. Then if you say, okay, then it's 20%, then they say, oh, this is ambitious. I mean, we have to sell this to our boss, and if it's then later is less, they won't like it. So they don't dare to do it. And then you say 30%, they say, well, braggart, get out, we don't believe this is following. And from this, it basically follows that you always have to say it's 15%. And the reason is, if you said 15, it's just in the middle, it sounds reasonable, but a lot. If you say 13 or 14, they say, how can you be so precise? And therefore, it's always 15%. And it seems to be a constant here. There's one other thing you have to remember. These people work a long time on this. If you come there and let's say you improve this by 50%, they look awfully bad, I mean, to their management. I mean, how could they work for 10 years on this and it's possible to do it 50% better? They will just hate you. And then you have no good cooperation. So 50% on the other side is also kind of safe for them, because 50% is a lot, but still kind of in a margin, and it doesn't make them look they didn't know what they do. So basically, it's irrelevant of the problem. Let us talk about pilot projects. Sometimes if you start with a company, they will suggest to do a pilot project and basically to gain trust and things like that. And you have to see this is kind of a one-sided affair, because actually it might increase their trust in you, but it will probably not help much to increase your trust in what they do. And the unspoken expectation is that you put in more resources than what you are paid for. And to my experience, I have to say that the chances for continuation project are as good with or without a pilot project. It just doesn't make any difference. The only difference it makes is if you make it kind of cheap to get it started and so on, you will have a lot of trouble getting up your prices again afterwards. They will just say, well, in this project we already did at that price, we can now not tell our management that it get twice the price or something like that. So this is really a problem. And if you really want to do something, then the default has to be continuation. I mean, just suggest you make a big project and there's kind of a milestone after some time, and basically there they can break off if it doesn't work out or something like that. But the default should be to continue, because the big problem usually with projects is get management confirmation and approval, and if you have to go through this all again after the pilot project, well, basically, as I said, chances are as good as before. Making a contract. Well, there are a lot of things to keep in mind. You have to see about deliverables, intellectual property rights and patents. That's pretty much of a topic, because patents get an increasing problem. I mean, traditionally in mathematics, once you have shown some result, it's open to everybody. They have to cite you, of course, but that's it. But with a patent, it's kind of different, because other people are not allowed to use this anymore. And I've seen algorithms patented, which is actually not allowed in Germany, but is in the US. And this leads to nobody citing it anymore or using it and just ignoring it, basically. Or having a kind of a mathematical projection, give it a different name, and then use it again without showing the connection to the other one. But anyway, open source there is a great achievement, and but there are all these non-fitting licenses, and there is a lot of problem on intellectual property rights, and it's not clear how to solve this. It will just be a lot of effort, especially if you then want to include third-party codes from somewhere else. There are different licensing terms and so on. That's kind of a problem. Then finally, if you make some nice industry project, it succeeds, they might even use it, and then who's doing the maintenance? I mean, your research institute or research place, you don't want to do maintenance, won't you? So what do you do here? Then you want the right to publish your results. I mean, imagine you save them 50% more money, then you say, oh, let's keep it secret and tell nobody, because we have an advantage compared to the competition. So that's bitter. You want to give talks about it and tell everybody that you succeeded. And you want the right to cooperate with others. There's a problem with NDAs and things like that. And if the project ends, either normally or even if it fails, you want the right to continue afterwards with others, and it might be even the competition. So what do you do with this? Who owns the data in the end? I mean, you need it to publish and have things like that. So there's a lot of issues to keep in mind, how to continue after the project ends. And what happens actually if the industry partner does not keep their milestones? I mean, the problem is that it's a collaboration project usually, so it's not just depending on you. Or you would need a contract that says, okay, you get everything beforehand, and then it's just on your side. But to my experience, this is very seldom, because once you start looking into the data, you will find issues and they have to correct, and that gives you a lot of trouble here. And remember, in the end, the contract for you is a bit useless, because you will never sue them. And so what can you do? I mean, if they don't keep their promises, okay, you can ask them to continue to pay or something like that, but overall I mean, usually the contract says that if it doesn't work out, the contract is cancelled and stopped, and this is not going to help you. So this is a problem. Yeah. Then there is the legal stuff.
The sublicensing right described in section 4.2 above shall include the right to sublicense the software to a financier for sublicensing to end users, or permit end users to sublicense the software to a financier. The rights described in A and B shall only be granted in order to enable a financing model for the licensee and the software for end users.
Here, this is actually from a real contract. Basically, this is gibberish to us, and this is kind of a problem. So then comes administrative stuff, same thing. For example, I got a form saying, is your product subject to the US Export Administration Regulation 15 CFR Part 730 to 774. I have not the slightest clue what this is about, but you have to take care of it. And either your administration does, but they usually don't know really what you do, or you have to take care of it. And this is just something you have to do. There's no way around. but it's no fun, honestly. Then it's about selling software. I mean, there are these things here like licensor remains liable to fully compensate the entity concerned for any damages, costs, and reasonable expenses incurred in connection with such third-party intellectual property infringement claims. Which means if you provide some software to a company and then somebody else you might not even know comes and says you're infringing their patents or whatever intellectual property rights, you might have to come up for the lawsuit. And I doubt you really want to do that, and this is much of a problem. On the other hand, you might do your project with a lot of whatever PhD students, student co-workers and so, and then you really would have to check where they get all the code from. I mean, you really have to write it yourself or something like that. Once you get a lot of people involved, this all gets a little bit of a nightmare. And yeah, well, one option actually is just to explore the method and then have a clean implementation by a company or something, maybe from somewhere else, and from a commercial software developer, and then you're kind of out of it. You just research the methods, but the commercial implementation is done elsewhere. And I have to say, this is actually a method that sometimes works quite well. Then there are lawyers. The company will involve lawyers, and your institute and university might do also. And lawyers like to dispute by attrition and exhaustion. I mean, they will not finish or converge easily. They often do not understand what the project is really about. They have no problem to argue at length about how to distribute the members of the empty set, and they are obsessed with low probability worst cases. So, I mean, as I said before, this is usually in a collaboration project, so if you're both mean to each other and hate each other, it's not going to succeed anyway. So there may be not so much use to handle all the cases. But anyway, they try to cover all cases without any formal methods and often without even understanding the concept of showing that all cases are covered. Just about, yeah, well. And so they usually will not converge unless by massive time pressure and or an order from above, which you have to ensure. On the other hand, you have to see they are necessary and it will take some time. You have to plan it, you have to support it, and I mean, they are doing their job, and without them you will not end up with a useful contract, and in some cases you really need this, and so, well, it's just part of the thing. Next is communication. Communication is one of the most important thing at all. So the problem is that a lot of people can say the same words but mean different things. I mean, you have to speak the language of the problem owner. About technical terms, mother tongue, their problem is your problem and your solution has to become their solution. That's important. You should not trust assumptions, because if they talk, they have a lot of implicit assumptions, but you don't know them. You have to ask. And you have in the end to convince both the decision makers and the tech people. It's not enough if you just convince one of them. And yeah, this is really the most important thing. As long as you understand each other, it's usually going to work. And you see, this is about how to describe the problem. This joke is, if I remember correctly, from the 70s maybe, if not older. And it's as true as it was then before. I mean, there's one thing what they actually wanted, how they described it, what the mathematicians then really understood of it, how it was modeled. As you can see here, the implementation at least make it workable. On the documentation and support, well, it's research, and in the end what was needed was something totally different. And this is happening again and again all the time. Finding out what the real objective of the project is really important, and it's usually not what you are told in the beginning. I had lately some discussion on a project and say, oh great, I can prove you can save 100 million euro, and they say, oh no thanks, that's actually not what we want and what would help us. Sometimes it's just difficult because the cost impact when optimizing virtual or existing infrastructure is unclear, so how much does a change cost? From an optimization objective, you always want a price for every possibility. But this is sometimes hard to get by, because if you want, let's say, build some stuff like a pipeline or so, then usually even just finding for a particular route the correct pricing is kind of hard. It depends on a lot of things, and so you will have to go with something much easier. And you're comparing often apples with pies and things like that. In the end, pre-processing is very important, because most real-world problems are rather big, at least to these academic toy examples. And the most important thing, or one of the most important things in the project, is decide what you have to model and what you can ignore or fix later in some way. This is really a key issue. As Schwatter said, the traveling salesman problem is to mathematical programming what chess is to artificial intelligence. Thoroughly useless and fiercely competitive sport that serves as a testing ground of your techniques. And this is what I want to explain you now here in the next slides. So let's talk about javelin throwing. Here you see the theory and the equations and everything. So basically from a mathematical point of view, it seems to be very clear. Okay, now let's see about sports. This is javelin throwing at sports. And as you can see, I mean, the javelin is normed. All the conditions on the environment is all precisely set. Also, the objective is totally clear. I mean, you want to throw it as far as possible in a particular direction. And the measurement, everything is defined. Very nice. So now let's look at real-world practice of javelin throwing. And this looks like this. As you can see, the clothing of the people is not perfectly, I mean, it's not really supporting throwing it very far because it's heavy, and actually it's not their goal to throw it as far as possible somewhere. And the whole thing is just, you see that sports is just a very simplified, generalized sport of it, while practice has a lot of details which have to be kept into account. So again, about modeling. I mean, how strange do you want to get? If you went somewhere to a real-world industry settlement, you will find very funny things like zone-defining origins, verzonende Ursprünge, which is something in telecommunication, which is something very particular. Or I just lately encountered a breathing sac in a natural gas pipeline network. And first, you have no clue what it is. It's not so clear whether you actually need it or if you can ignore it. And always, if you ask your industry partner at the end, they will always come up with, well, we have one location just left where there is this old whatever and it behaves totally different from all the other stuff I told you. And the problem is you have to decide what you have really to put into your model so you get useful results and what you can just ignore and then maybe in post-processing or otherwise fix later. I mean, a lot of things, engineers usually know what they do, so a lot of things just work out right. And you just have to check, and most of the time it will just be okay, and you can just fix a little bit later on. The important thing is that you think and act problem-centric. It's more important to solve the right problem than to solve the problem right. So identifying the problem is half of the way to the solution. And the good thing is you find the problem, you see all the solution methods, and then you choose what is actually the best method to solve this problem. Unfortunately, the way it is, if let's say your university is very famous for this particular method, then you will say, oh, this is my solution method, and then you will fit the problems to it. And it's a bit of this, well, if I only have a hammer, then everything around are nails attitude, and this is not going to give you the best results. Let us come to the project setup, what I would call the classical approach. So first here we have a problem to solve. See the problem there. And what do? Well, we have a teacher, that would be the professor, for example, and you have a very determined PhD student. And now the student, supervised by the teacher, attacks the problem, and well, then he fails or succeeds. And if in trouble, the teacher can usually rescue the project or send another student to attack the problem, and And this is what we call the classical hero approach. You have your hero, you send him in, and then, well, he slays the dragon or not. And this is fine, but sometimes there are projects which are just too big to be tackled by a single hero. So you need a team actually for this. And I have to say that in my experience, mathematical research usually has no suitable infrastructure to run big projects with non-disjunctive tasks where you need, for example, 10 people working on the same topic for a long time, cooperatively. I mean, you will see some in the other talks of this workshop, but nevertheless, overall, it's kind of a bit of a problem. And But there are a lot of difficult problems where you have to cooperate, where you need other institutions, and this all does not make it any easier. Now let's come to one of the most important things at all. This is data. I mean, we are all going towards a data-driven world, environment, society, whatever. So data is kind of important now. And would you think that a cellular network operator knows where its base stations are located? Well, I would think so, but then I found they actually didn't know, because they subcontracted erecting of the base stations and they give just a list to the company to erect them, and they do an arbitrary order, so the cellular network operator just is notified once a base station is actually coming up, but sometimes even later. You would think that a fixed network operator can tell whether parts of the networks are connected. Yeah, I thought so, but then I got the data and actually it was not connected. Well, and I had some other experiments where a chemical company actually found a plant when they made some research. They just had lost it, and later on it turned out there was one more than they thought. And we had data where a 5 meter long pipeline had a height difference end to end of 100 meters. Well, you find everything. And many companies have their data in Excel, and there's no formal validation or referential integrity check or anything. And well, actually, if they do formal validation, then it's usually so restricted that they are missing some fields or something. So they start to reuse data fields and say something like, oh, well, yeah, this field means A, but if there is 999 in the field, then it means something completely different. And well, I can only say if you're not finding at least one error per 100 data sets, then you're not looking hard enough. And the biggest problem actually is that the data changes all the time, because I mean the world is not stopping when you're doing research. So you get a data set in the beginning, and then while the project continues, it changes. And this is something where I have to say we're not very good at coping. You might have a data set, then correct all the data, and then you get an updated data set which has all the errors again. It's really not that easy. Furthermore, actually they might not want to give the data to you. So for example, if you said in the beginning, oh, I will improve the performance by 50%, well, yeah, as I said, they hate you, and probably whatever you get will be pretty much garbage where you cannot show. All the data might not exist. I mean, it's not all new .com area companies which have sensors and everything everywhere. There's a lot of companies doing solid business for a long time, and it's just solid engineering, and there's not so much sensor and data, and it might take time to get it and everything, even if they want. Also, usually systems are kind of layered. I mean, there's a contract department, and they have a view on the network, on a contractual view, but this might be totally different from the network operation department, which is a totally different view. And nobody ever was consolidating this data because there was no need for it. Now you say, okay, we need it, but this gives a lot of problems then. And so I have to say the first results of all the optimization projects I have conducted so far was usually to improve the quality of planning data available at the company. And some appreciate that, some were not so happy because of the cost involved and so on, but nevertheless, if they do a project with you, they learn a lot about themselves. This is the first thing that happens. And here is from a data scientist report. What you see here is basically that this part, which I would call cleaning the data, altogether is over 80% of everything. So basically, as a data scientist, you are cleaning the data. And once it's all finished, you have some, well, maybe less than 20% where you actually look into it. Now, finally, the project is somewhere and you get actually a solution. That's kind of great. So one thing is that optimality is often not required. Industry is usually more interested in reasonably good solutions in short time than a proven optimal solution after a long wait. And to compute a gap or proof infeasibility is quite important, because what happens several times is that you go to the company, say, oh, we have here a new solution, and they look at it and say, well, yeah, but actually originally what our planners did was better. And if you then have proven optimality, you're kind of irritated and check and find out that the solution they computed are actually infeasible. because they didn't adhere to all the rules they gave you. And if you are just get some solution, then it's much more difficult to immediately see that what they do there is not feasible. So this helps you a lot. Another thing is, it's very important that your solution is too optimal. Because too optimal is what you can spot if you just display it. So if you display a solution there which is not too optimal, but I mean just by a very small margin, one of the experienced people will just point there and say, oh, here, you could switch these two things and then it gets better. And at that point your reputation is done. Even though it's actually only 1 promille getting better, it doesn't matter overall. It's obviously clear that you have missed an obvious spot to optimize. So you should take care of this, because once it's more, you need more than 2 optimal, it's not so easy to spot. The other is, as mathematicians or optimizers, usually we compute extremal solutions, while engineers usually prefer kind of 80% solutions, more robust stuff. So imagine you have 5 machines, and in the end you can either run 4 at 100% or 5 at 80%. They will probably in reality prefer the 5 by 80% thing, because it's just much safer than the one where you have 4 and then maybe to switch on and off the 5th all the time, depending on the variations. And then finally you may get very, very strange solutions. And the reasons might be there are anomalies, errors in the data. There might be difference between model and reality, and you might reaching capacity or cost thresholds. I mean, all these knapsack constraints are always a bit critical there. And then finally it might be that the result is just different from what you expected. Here's an example of it for an unstable solution. You see A, it is an optimal solution there, and then you here just change the data very little bit, and after the small change, immediately, I mean, the optimal solution is completely different. And this is usually not liked much. Or here you have a strange cost function. So basically for a given distance the cost is constant and then jumps somewhere. And this leads to a lot of strange results then, because I mean up to a certain distance everything doesn't matter, and then just having 1 meter more makes all the difference, and then it doesn't matter again, and this gives you quite funny solutions there. So here you see an example for some strange solutions. So why is nothing connected here to B? Well, the reason is actually that everything is just in the vicinity of B and C. C has enough capacity, and so everything is just connected to C. But why is B then active? Well, it's required from the input data. And why are some connected in the vicinity to C directly connected to A? And this again has to do with the distances, whether you use beeline distances or transport network distances. And so it really depends a lot of the data, and you have to check carefully all the results you get, or they will look kind of strange. Same here. This result, which for an optimal connection of nodes to higher level nodes, is actually optimal. But as you see, I mean, why is F connected to A instead to D? Why would E be better to A than connected to F, and so on? Actually, I checked everything, and within this model this is totally correct, but if you present a result like this, they might look a bit irritated, honestly. So then we have the run of the project. And one thing that is quite interesting is actually the bigger the company, the more unstable is the department. I can remember sitting with a small company at network division at the time, and they said, well, yeah, you're such a small company and we're not there, we don't know whether you're around in a few years. And the truth is, this company is still lively and around, but has been sold for a long time and sold again, and basically not existing anymore. And so once a company is really big, or let's say like another big thing, then smaller departments can actually vanish quite fast. If the project takes too long, they may lose interest in it. So there is a time limit. I mean, making a project over 10 years will have changes of managers and so on, and they will just forget about it and at some point say, well, maybe we don't need it anymore. Then it is research, not development. And so it's not so clear what the results are and how, I mean, they are not coming in a linear way. I mean, in my experience, research results come in a step thing. Nothing happens, you think and think, then somebody has an idea, gets a lot better, and then continues. While management usually likes some linear progress, which gives you predictability. Milestones in the beginning, I mean, I had 5-year projects where we had to set milestones for the whole project, and honestly, this has never ever worked. And yeah, as I said, the original solutions the company have might be infeasible, but then you have to adhere to all the rules, and then it gets a bit complicated. In the end, you have to check the solutions, because we do errors too. So sometimes you compute something, it's complicated, and nobody looks at it, and then it's just wrong. Here's something about the requirements of real-world applications, and going from pure research to applicable research, that is something you could in theory apply but you don't, to applied research, to a case study where you really then do something, to a planning application, to a control application. And if you see the requirements increase more and more. So in the one case, I mean, you just do your own problem definition, you have generalized, simplified ones, and if you're doing control, it has really to be a complete problem definition. Same for real-world constraints. And in the extreme case, I mean, if you're just doing pure research, you don't care about real world, right? And if you do a control application, you just have to keep them all. For the data, it's the same. With a case study, you might get away with some simplified data, which is nice. The more practice or regular you get, the better the data you need. And the same is for the code. I mean, for a case study, it just has to run once, and whatever you do is fine. If you have a control application, it has to run 24/7 and has to be really professional. And this is something which is quite a requirement. Let me end with a slide from Guido Sens, who asked how to make optimization solutions work in industrial practice. Well, and basically his answer was, you need the right people with the right mindset. And industry is full of optimization problems, but sometimes or often they are not obvious, and identifying is part of the job. Excellent mathematics which fits the challenges of the application is necessary, but not sufficient for success. And yeah, as I said, you need the right people who really want to solve the problem. And what he asks is, why isn't it considered innovative if a solution works in industrial practice? Because there is really a huge gap between something done just in research and showing that in principle you can solve traveling salesman problems or whatever, and on the other hand, I mean, having something that really works in an industry project. And so I really end with a quote from George Danzig, who said that the final test of a theory is its capacity to solve the problems which originated it. And this is basically the motto we have here for a long time. Thank you very much, and I hope you enjoyed the talk.